Hello, AP Chemistry. So we are returning to Unit 3, and we are looking at the gases. All right, so we're starting with my favorite joke. Do you have any history of mental illness in your family? My uncle used the ideal gas law on a liquid. All right, so we're specifically looking at gases right now. The enduring concepts, gas properties are explained macroscopically using the relationships among pressure, volume, temperature, moles, and the gas constant, and molecularity by the motion of the gases. So what that means, long story short, ideal gas law. PV equals nRT, Pivner. R is a constant, the gas law constant, 0.0821. Liters times atmospheres divided by moles times Kelvin. So the gas constant dictates the units we use. So we always have to use atmospheres of pressure, liters of volume, Kelvin for temperature, and moles for the number of moles. There is another gas constant, 8.314, and that is in kilopascals, but it's not very common. All right, all of those factors contribute to the macroscopic behavior of a gas. So how much space the gas has to exist in, how fast the particles are moving, that's temperature, how often they're colliding with the walls, that is the pressure. There's also the outside atmospheric pressure, all right, pushing against it, and how many gas particles are in there. So Pivner, important equation, and from there we can derive all of our gas constants, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law of volumes. All right, so they're all there. All right, now another important equation that we need to have for the gases, all right, in a sample containing a mixture of ideal gases, the pressure exerted by each component is independent of the others. All right, that is Dalton's law of partial pressures. So if we have two gases and we combine them, all right, their pressures will add up. They are not going to interact with each other, all right? So we're going to have more collisions with the walls. We're going to get a greater pressure, all right? So we can do that. The partial pressure, it's either the total pressure times the mole fraction, we've seen that, or we add up all the partial pressures. In this picture here, right, we have 1 atmosphere of pressure, 2 atmospheres. When they're added up in the same container, we now have 3 atmospheres. It's just the total pressure. All right, here we're giving gauges in the pictures. In this picture, they are using weights to symbolize the pressure. It's not a common visual representation, but it is used sometimes. The more weights on top of the container indicates a greater external pressure, and so the pressure inside is equal to it. All right, so we're adding the 0.6 moles of H2 with the 1.5 moles of He, and we're getting a total of 2.1 moles of gas. All right, remember, the ideal gas law does not care what the identity of the gas is. All right, we'll talk about real gases when we get there, but it's not so important. All right, now, the last thing I want to say about the partial pressures, we've seen these questions before where there is 2 containers, right, gas in either, and there is a stopcock that is opened. All right, when that occurs, these often lead us to a Boyle's law type question where gas A, for example, now is existing in a larger volume, right? Instead of it being at a certain pressure for volume 1, it's now going to exist at a new pressure for volume 1 plus volume 2. So we've seen those types of questions before. I would review those. I would think about those. All right. And the last thing, this is really important. All right. I think that this shows up quite frequently throughout the years on the AP chemistry exam. This is a very classic experiment, gas collection. All right. So in this example, they're doing zinc plus hydrochloric acid. It's generating hydrogen gas, several different reactions. Any reaction that generates a gas in a lab, we typically collect it over water, right? So it displaces the water, it pushes the water down out of an inverted container, and we could measure the pressure, we could measure the volume of that gas. But the important thing to remember is that is always a wet gas. So there will be some water molecules just due to the vapor pressure of water, right? And we will often be given the partial pressure of water at different temperatures. We always have to subtract that from our measured pressure, which will be atmospheric pressure. in a gas collection lab, we always have to just subtract the partial pressure of water. So classic experiment, we'll be looking at this gas collection. All right, so make sure the worst thing you can do is forget to remove the partial pressure of water. All right, now, graphical representations of the relationships between P, V, and T and N are useful to describe gas behavior. Boyle's law is the only inverse relationship, pressure and volume, so that is a constant. So as one of them is really big, the other is really small, inverse relationship. Volume and temperature have this constant, have this direct proportion where they increase. Charles' law only works if we're at constant pressure, right, which sounds weird, but keep in mind a flexible container is always at constant pressure because the container can adjust until it reaches a point where the inside collisions are equal to the atmospheric outside collisions. So Charles' law, this direct relationship between volume and temperature, always for a flexible container. And keep in mind, think about the hot air balloon, right? The hot air balloon's volume can change. Gay-Lussac's law, it's where pressure and temperature have an increasing relationship, right? We increase temperature, the particles move faster, they collide with the walls more often. This only works for a rigid container. Think about like a scuba tank. It's made of steel. The volume cannot change unless considerable stress has been put on it. So no matter how many collisions we get inside of the container, it's not going to be affected by the outside collisions. All right. So now, the kinetic molecular theory relates the macroscopic properties of gases to motions of the particles in the gas. The Maxwell-Boltzmann distribution describes the distribution of kinetic energies of particles at a given temperature. All right. We have not mentioned the Maxwell-Boltzmann distribution. I think we saw it just briefly, but I'm going to go over it real quick. All right, it kind of looks like all of those graphs you may have seen in the news about flattening the curve. All right, but here's how a Maxwell-Boltzmann distribution works. All right, for any gas, all right, not every particle is moving at the same speed. All right, some particles are moving faster, some particles are moving slower. There is a whole, a whole range of speeds that the gas can be at. In a colder gas, the largest number of particles, the average, is going to be lower. And the distribution, it's going to taper off real quickly. All right, so when we have colder gases, the average, which is going to be the height of the peak, is going to be much lower, right? The average cold gas particle has a really slow speed. Some of them do have faster, and some of them do have slower. In a hotter gas, the average, and again, that's the top of the peak, the average, it's going to be shifted over. So more particles are moving at a faster speed, all right? And the way that distribution occurs, it spreads them out a little bit further. So we're going to get more overall particles with faster speeds in the hotter gas. The average will be higher than the cold one. We'll get more faster, and we will have less at the slower range. All right, so just another example, a cold gas, it spikes up really high. That's like when you get a huge increase in the coronavirus, what we've seen in the news. All right, gas at room temperature, it's spread out a little bit lower, and a hot gas, it's spread out the most. All right, and again, it is the peak of these curves that represents the average speed. All right, and that's what we think of as like the average temperature. All right, some scientists, when you get really deep into the nitty-gritty, they'll actually say that the speed is actually a little bit ahead of the average, so it shifts over just a little bit due to different interactions going on, but that's not necessary for us. Just remember, because the x-axis represents speed, it's the average speed. Some will be ahead, some will be below. But when we have a cold gas, we don't get that far ahead, whereas when we get a hot gas, we get a much wider distribution. All right, one last time, not that we're talking about chemical reactions in Unit 3, but as we increase kinetic energy, this allows for things like chemical reactions to occur with greater ease because more particles will reach the activation energy. All right, so we can use it interchangeably for temperature, which is we can use as speed, or kinetic energy, because kinetic energy is based on speed. All right, here is our formula for kinetic energy, 1/2 mass times velocity squared. All the particles in a sample of matter are in continuous random motion. All right, and again, some faster, some slower. The average kinetic energy of the particle is related to its average velocity by the equation. Ke equals 1/2 mv squared. We will not solve for this, so you don't have to worry about that. And we can compare two gases at different masses, but we're not really going to worry about the mass changing in one of these questions. It's more so how can we change the velocity. And again, the only way to change the velocity is with the speed. And I just wanted to show you in this picture, it's important that like the tail of the particle showing it in motion, if you draw a longer tail, that's going to be assumed that the particle is moving faster. All right, so this is my slow gas, this is my faster gas, just based on the way it's being visualized. And again, those tails aren't all necessarily going to be the exact same length because not all the particles are moving at the same speed, right? There's that distribution, that Boltzmann-Maxwell distribution. All right, now the Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. All right, so that's just saying that anytime we get a thermometer reading of a sample, especially for a gas, that thermometer reading is really telling us how fast those particles are moving. So at low kinetic energy, it's not moving very fast. It doesn't have many collisions. Our thermometers will read low temperatures. And when they speed up, right, our thermometer will expand. We'll get a much higher temperature. All right. Now, this is kind of an important one. The ideal gas law does not explain the actual behavior of real gases, right? Ideal gas law only for ideal situations. All right, let's keep it real. Real gases deviate. Some of them deviate lower, some of them deviate higher. In the end, as we increase the pressure, all of them deviate above. A lot of the deviations are measured for the ideal gas. It's based on pressure times volume. So as you change the pressure, their volumes kind of start to freak out a little bit. All right, deviations from the ideal gas law may result from interparticle attractions among gas molecules. All right, so we assume that there's no attraction in the ideal gas law, but in reality, when they come close to each other, there can be some attraction. All right, particularly at conditions that are close to those resulting in condensation. All right, if a gas begins to condense, it's switching from the gas phase to the liquid phase, and it's actually starting to have like a noticeable volume now. All right, so just again, when we have no intermolecular forces, these gases move in straight paths, but when there is attraction, they'll kind of curve, right? And they kind of slow down each other, and so that's why sometimes we get a pressure less than what we would expect. All right. Now, I want you to think about something. When are the particles going to interact with each other more? All right, when they're closer together. So at high pressures. High pressures are bad for our real gases, right? As the pressure gets bigger, that's where the deviation is going to get bigger. So high pressure is bad. If we want a real gas to behave like an ideal gas, we want a very low pressure so that they're not close to each other. All right, and we want to hold off. We don't want that condensation to happen, all right? Because if it begins to condense, it'll change our volume on us. Now, when does the condensation happen? At lower temperatures, all right? To prevent the gas from being at lower temperatures, we want a real gas at a really high temperature so that it can behave like an ideal gas, all right? So this kind of summarizes, if we have a real gas, at high pressures and high temperatures, it'll be similar to an ideal gas, all right? Low pressure, at low pressure, we want high temperature. Low pressure is good for a real gas to behave like an ideal gas. At a high pressure, it starts to move away from it a little bit. We do want that high temperature, all right? So sorry that that's a little confusing. So for a real gas to behave like an ideal gas, we want high temperature, so it doesn't condense, and very low pressure so that they're not interacting. All right, deviations may also arise from particle volume, particularly at extremely high pressures. All right, so that's bad. So answering AP questions on gases, the do's. Mention collisions when talking about the pressure of a gas. All right, anytime you're answering a question about the pressure of a gas, that's the collisions on the walls. All right, so if we're thinking about kinetic energy, if we increase that, either we can say the particles are moving faster, they're hitting the walls more often, or they have more kinetic energy, they are hitting the walls with greater force. Do mention speed of molecules when talking about temperature. If we've increased the temperature of a gas, the molecules are now moving faster. If we decrease the temperature, molecules are now moving slower. Mention attractive forces when discussing real gases. All right, if we're worried about why something's deviating, talk about the attractive forces going on between the gas particles. All right, remember, the more polar molecules will deviate more from ideal behavior, right? The more nonpolar gases will behave more ideally. All right, and do show setups when performing a calculation. So if you're doing something like a Charles law or a Boyle's law, showing that setup is always a good idea. All right, and anytime you're using the ideal gas law, show that setup, right? And it just kind of helps you make sure you plug in everything correctly, because those are usually very simple calculations relative to everything else in the AP chemistry curriculum. So you never want to make those simple mistakes. So just show your setups. And then the don'ts. Don't forget to convert Celsius to Kelvin. A lot of the questions will give you the data in Kelvin, but that is a very simple mistake that you will lose points in a free response. All right, and don't assume all particles are moving at the exact same speed. All right, the College Board will bait you with that. All right, they expect you to know that there's a distribution of speeds and that the average speed is correlated with the average temperature. All right, but they will sometimes include that in a prompt or in a multiple choice question. And if you ever see something where it mentions specifically that they're moving at the exact same speed, that is incorrect. So don't fall for that answer. So these are our gases. This should be a nice, simple topic. All right, just in reviewing it, you're gonna wanna do a little bit of practice. Just do some of the questions out of the textbook just to kind of have it down, but the ideal gas law should be very straightforward.